All right. So let's say section 2, right? So we're now in section 12.2, okay? So y'all can see that, okay? We're going to talk about the second derivative now. Now that you got the first derivative down, the second derivative, all it is the first derivative of the first derivative, right? So the math is, you've already got the math down. It's just interpreting it. So let's look at these two functions here. They're both increasing, right? I mean, the slope everywhere is upwards for both of those functions. But you can tell they're increasing differently, like that versus that, right? They're both the first derivative for both of these is positive, right? They're increasing. But the rate at which they're increasing is different, right? If you look at this one here, it's positive, more positive, even more positive, even more positive. What that means, the second derivative is positive, right? The rate of change of the rate of change is positive. This guy, the slope is positive, less positive, less positive, less positive, right? So here the second derivative is negative. That makes sense? So just the first derivative isn't enough if you're like trying to make the most out of your investments, right? You keep looking at your stash account and you're like, okay, yeah, it's going up, but you want to know at what rate that it's increasing. That kind of helps you predict, because eventually this thing here looks like it's going to start going down, doesn't it? Yeah, it's still increasing, but the rate is like it's diminishing, right? So you kind of want to be able to see a little bit further ahead, right? You want this one, not that one. So what this tells you is concavity, like graphically, this would be concave down, this would be concave up, okay? So you can see here, the slope is positive, less positive, less positive, it's finally zero, and then, so here, the derivative is, the second derivative is negative. So when you see concave down, that means the slope is decreasing. And this one, second derivative, will be positive, because here the slope's negative, then it's zero, and then it's positive. So it went from negative to positive, right? So that's what this whole section's about. You already have the math. Mainly, this is going to be about trying to do word problems, right? Trying to analyze this stuff correctly. Right, this class is hard, right? Like the Cal 1 has more math in it. It's all more nitty gritty math, but y'all have all these other vocabulary words. Because you're actually doing applied math, not just pure math. You're applying it to business. So you have all those marginal averages and average marginals, and that was the hardest part on that exam 1, right? Like the last problem, it was the marginal average. So you had to take the derivative, not of the function, but of the function divided by x. That's what most people would miss. They'd see marginal, take the derivative, but that wasn't the right function. So higher derivatives here. So we'll get into some notation, because there's notation, right? So if this is f, you could take the first derivative, you get this, right? I could take the derivative of that, they call it f double prime, right? I could take the derivative of that would be f triple prime. And then after 3 of these primes, it starts to look stupid, okay? So they'll put higher derivatives in parentheses. Yeah, they have 4 in parentheses there, right? So if you just wrote that, that would mean f to the 4th power, an exponent. This is not an exponent. They put those parentheses there specifically so you know we're talking about the 4th derivative, which you hardly ever do, okay? So in physics, if you have your position function, like say s is your position at time, right? Then your velocity is your change in position, right? Your position's changing, you're moving, right? And then your, that's your velocity. So your acceleration will be your change in velocity, which is the second derivative of position, right? So that's this in physics terms. And you can keep going, right? The third derivative is called the jerk. That's what gives you whiplash. And then you have the fourth, fifth, and sixth derivatives, which are called the snap, crackle, and pop. Okay? And in physics, you hardly ever use those. But you notice here that for a simple polynomial, if you take enough derivatives, eventually you get zero, right? The rate of change of the rate of change of the rate of change eventually goes to zero. And you can keep going, but it's always going to be zero, right? Other functions aren't like that. Some of them you could take derivatives forever. So the rate of change of the rate of change of the rate of change could go on forever and ever. We'll see examples like that. So some notation here. So f, right? If we take the derivative of f of x, we get f prime, right? Well, if we take the derivative of that, we get f double prime, right? Well, writing this out sucks. So they write that as d squared dx squared, okay? That's not an exponent, okay? d dx is an operator, right? It takes a function in and gives you a function out, a different function. It maps f to f prime, okay? So a naive student might look at this and say, this is d times x squared. No, it's not d times x squared. That doesn't make any sense at all. What is d? D's change in, right? D means change in something, right? This is the change in f with respect to the change in x, okay? So, I mean, it kind of looks like dx squared, right? But it's not what it is. You're applying the operator and then applying the operator again. So again, just notation. Like we run out of like ways to write stuff, right? So eventually we have to start using context to interpret these symbols. Okay. All right, so a picture of that in the notes. We could talk about f double prime, y double prime, or d squared, y dx squared. And for derivatives higher than the fourth, we just put parentheses around whatever derivative we're talking about. Okay. With example. Find the second derivative. Well, the first derivative, 3 times 8 is 24. 9 times 2 is 18. 6. So that's your first derivative. So we take the derivative of the derivative. That's our second derivative. Easy, right? Right. The math is the easy part. Let's look at part B here. Okay, well, let's see. Y prime, let's see, we have to use the quotient rule, right? Which is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And now we're going to want to take the derivative of this. So let's go ahead and do the algebra and make it as pretty as we can, right? So y prime, let's see, we have 12x minus 4 minus 12x minus 6. Okay, those go away. We got negative 10 over 3x minus 1 squared. Made it as simple as we can. Now we want to take the derivative of that. I don't want to do the quotient rule. Quotient rule sucks, right? It has fractions. I don't like fractions. So let's just rewrite this as 3x minus 1 to the negative 2. All right, there's no x's up here. That's just a number. So now we'll just use the power rule, right? The y double prime would be 20 3x minus 1 to the minus 3 times the derivative of the stuff on the inside. So this would be 60 3x minus, right? Piece of cake. And we could keep going, right? Let's do the third derivative. 60 times negative 3 would be what? Negative 180 times 3x minus 1 to the negative 4 times 3 again, right? So you notice because every time you're subtracting one from this, you could keep going forever. This thing has an infinite number of derivatives. And so that's kind of like a class of functions. There's some functions where eventually the derivatives just are 0. Other functions, the derivatives go on forever, but you can see there's this pattern. You're still getting this 3x minus 1, the higher and higher powers on the bottom of the fraction. All right? Okay. Oh, this one's cool. Let's look at this one. All right, so fine. Product rule, right? We have the first function times the derivative of the second plus second function times the derivative of the first. The derivative of x is just 1, isn't it? Okay. So this is exactly what y was, wasn't it? All right. This is y plus e to the x. The extender is going to repeat itself. So if we do y double prime, let's see, the derivative of this, we already know the derivative of this. The derivative of this is this, right? The y double prime, the derivative of this thing is all of this, and then we have plus the derivative of that. Okay? So y triple prime, we know the derivative of this, again, is that. And then the derivative of this and the derivative of that is just those again. So what it looks like is the nth derivative is just this, and then you have n of those added to it. Now we have a formula for any derivative we want. Of course, when you see something repeated like that, you'd want to factor out the e to the x to make it pretty, right? So this one here would be x plus 1, 2, sorry, x plus 2 e to the x, right? So this is just 3 e to the x, so this one's x plus 3 e to the x. Just like this one is x plus n e to the x. Is that okay? Right? So you get these cool patterns that can go on. Now you're starting to see the poetry in the mathematics. Imagine Shakespeare trying to fit his words into iambic pentameter and not sound stupid at the same time, yet still get a story across. There was more math there than there was like English, right? So let's see if we can make some sense out of this guy. Okay, suppose that over a 10-month period, the price of stock A is given by f of x and the price of stock B is given by g of x. See, for this problem, I would have used the letter t instead of x because we're talking about over a period of time, right? I like to use t for time instead of x, okay? So we're assuming here that the units of x is months. Since they said it's a 10-month period, I'm assuming that they should explicitly say these things when we set up the problem. But when are these stocks increasing? Well, they're increasing when the derivative is positive, right? That's when they're increasing. So let's find f prime. This would just be 1/2 x to the minus 1/2. And let's see, we could write that if we wanted to, like this. And then g prime, let's see, 3/2 times 0.1. 3/2 is 1.5, right? And then multiplying by 0.1, that's like dividing by 10, right? Multiplying by 0.1. So that would be, instead of 1.5, that would be 0.15 x to the 1/2 power, or 0.15 square root of x. So the derivatives are easy, just with the power rule. The hard part is solving inequalities. They want to know, when are these increasing? Well, when is this, when is this increasing? All right. So here's the analysis. Well, the number 1 is always positive, right? So really this thing is, when is this positive? Well, 2 is always positive, so this is saying, when is the square root of x positive? Well, the square root of x is always positive, right? So of course we can only plug in positive numbers, right? So f prime is positive whenever x is positive, right? It's not even defined for negative numbers. You can't take the square root of a negative, right? So basically it's always increasing. And of course we're not considering negative time here, right? These functions are only valid apparently over this 10-month period. So these functions are really only defined or valid or true when x goes from 0 to 10. Okay. Let's look at g prime. So again, when is this positive? Well, 0.15 is always positive. So when is the square root of x positive? Well, it's positive for any positive value of x. The square root of x is always positive, except for 0, right? Times 0. So that's when they're increasing. So that's the easy part. Now is when they get weird with the vocabulary, right? At what rate are these stock prices increasing in the 10th month? So in the last class, I made the mistake. I was like, okay, well, we just plug 10 into the first derivative, right? The first derivative tells us the rate of change, right? But they have, at what rate are they increasing? They want to know about the rate of increase. They're asking about the change of the change here. Real subtle, right? So here they're asking about the second derivative, all right? So at x equals 10. So what we need to do here is find the second derivative and then plug in 10. So the second derivative of this guy would be a negative 1/4 x to the minus 3/2. G double prime would be 0.15 divided by 2, that's x to the minus 1/2. All right, just doing the power rule here. So they want to know the rate at the 10th month. So we would just plug in 10 for x. Okay. I don't know what these are. I could plug them into a calculator. Tell you, since they've already done the math. Let's look at their math here. They've gotten the values. So f double prime is negative and g double prime is positive. So what does that tell us? That means that f here, even though the first derivative was positive, right? It was always positive. We just saw that f and g are positive for any value of x, right? They're always increasing. This says that the rate of increase, right, is decreasing. Yeah, the rate of increase is decreasing because it's negative. What that means is this thing looks like this. This one being positive says it looks more like that, right? Both of these are increasing, but the rate of increase is decreasing for this one. So the rate of increase for stock A is negative, meaning its price is increasing at a decreasing rate. And then for stock B, the second derivative is positive, so its price is increasing at an increasing rate. So you want stock G, not or stock B, right? That's the good one. That's the one that's not only going up, but the rate at which it's going up is going up. So since y'all are business majors, let's look into this paragraph here. So example 2 is much simpler than real life. Second derivatives are actually used by some investors. Imagine the ones that are any good at their job, right? So I imagine there's a lot of investors out there that don't know any calculus. Yeah, I don't trust them at all. All right, according to the Wall Street Journal, many investors hope it will help them get into the market ahead of any big rallies. In essence, the second derivative approach involves looking at such things as profit warnings, analyst earning estimates, and equipment orders, including cancellations, for signs that the downward momentum is slowing. And I already talked about the role that it plays in physics. Right? If you're going to be a good investor, you'd want to look into the third, fourth, and fifth derivatives, right? You really want to be able to project, see what's going on. All right, this one. So S here tells us the position to beat at a given time. Find the velocity. Well, the velocity at a given time is going to be the derivative of the position, or the change in position with respect to time. This would be 3t squared minus 4t minus 7. All right. And of course, we could find the acceleration. The acceleration is change in velocity, the second derivative of s. So we get this is 6t minus 4. All right. And then they ask you, when is this 0? When is the velocity 0? All right, well, since this is the velocity, they're asking, when is this 0? And y'all know how to solve this, right? You could use the quadratic formula, or you could do factoring. Y'all remember your trick for factoring? Factoring by grouping? Go ahead and do a quick recap. If you can't eyeball it to factor it, and you don't want to bother using the quadratic formula, what you do is you look at A times C, and you look at B. A times C is negative 21, and B is negative 4. So what we need, I'm going to call them P and Q. We need two numbers that multiply to give me the negative 21, but add to give me the negative 4. So if we can find these numbers, then this dude's factorable. So if I think about this, negative 7 and 3, they multiply to give me negative 21, but they add to give me negative 4. What these numbers do is tell me how I can break that up. So I would write, instead of 4t, I would write minus 7t plus 3t. And what that does is allows you to factor by grouping. I'll treat these things separately. Out of the first two thingies, I could pull a t out, and I get a 3t minus 7. Then I look at this, and I need to write that as something times 3t minus 7. Well, it's already 3t minus 7, right? So I'll write it as 1 times 3t minus 7. So what do I have here? I have a t, and I have a 1, and they're both multiplied by 3t minus 7. So what that says is either t is minus 1 or 7/3. And now we don't want to talk about negative time really. So really we're talking about 7.3, and in this case we're talking about seconds. At 7.3 seconds is when the velocity is 0. So in physics things are weird, like gravity, right? You might not realize it, but you are accelerating upwards at a rate of 9.8 meters per second. But your velocity is 0. You're not moving, right? which is kind of weird. Like, how can you take the derivative of 0 and end up with something that's non-zero? Something to ponder. That's how gravity is. Like, if you're driving at a constant speed in your car and it's pitch black out, or you can't see out your windows, you don't know that you're moving at all. Not until you accelerate, right? That's when you feel the force. You push back into the seat. Well, the force that's pushing you down, right, is really you accelerating upwards, right? That's what makes you feel like you're being pushed down, just like in a car. That's why physics is fun. All right, concavity. I already told you about concavity, right? So let's look. They're going to give us a whole bunch of pictures and pages going over this simple concept. We'll look at it again though. Over here, the slope is positive, less positive, less positive, negative, right? So over here, the first derivative is positive over here, but the second derivative is decreasing, right? Even here, it starts, the slope is 0, and then it's negative. So all the way between here and here, the second derivative is negative. That means it's concave downward. For upward, the slope is negative, 0, then positive. So the slope is increasing. So the second derivative is positive. So if it's positive, it's upward, concave upward. If the second derivative is negative, it's concave downward. And right in the middle, where the second derivative is 0, that could mean an inflection point in between where you're going from up to down, right? We call that an inflection point, right? Sometimes the second derivative is not defined, right? If you get your function for the second derivative and there's an x on the bottom of the fraction, you can't plug 0 in, right? So sometimes you have issues like that. Let's look at this a little more closely. Same thing with different pictures. It's concave upward, right? The first derivative is negative, first derivative is 0, the first derivative is positive. But everywhere here, second derivative is negative, positive, right? Concave upward, second derivative is positive. Because the slope is going from negative to positive. The slope is increasing. All right, so here we have this inflection point, right? So here it's concave downward, and then it becomes concave upward, right? So over here, second derivative is negative. Over here, it's positive, and at some point right in here is where it's 0. Okay, this guy over here, concave downward. Over here, it's concave upward. But right here at that point, f double prime, it's not 0. It doesn't exist, right? Remember those points, pointy points, the derivatives aren't defined there. So you can have stuff like that. I'll throw this picture in there. So here's another picture of the same thing with a whole lot more words to explain the same thing. Okay. More pictures of the exact same thing. So of course they say you can test for concavity by taking the second derivative and figuring out where it's positive and where it's negative, right? Wherever it's positive, it's concave up. Where it's negative, it's concave down. Let's see if we can do an example here. Find the intervals where it's concave upward or downward, and find any points of inflection. Well, first off, we need to get the second derivative. First derivative, see, 0.5 times 3 would be what, 1.5? And then 2 times 2 is 4. There's our first derivative. So our second derivative would be 3x minus 4. So when is this positive? Well, it's positive whenever 3x is bigger than 4, or when x is bigger than 4/3, right? So that's when it's positive for this. So that's when it's concave upwards. That means it has to be concave downward in the other direction, right? Because on the other side of this thing would be negative, right? It's when it's negative. So right at 0, no, not 0, at x equals 4/3, you're going to have an inflection point, right? So it's concave upward and then concave downward, and then there's at 4/3. Does that make sense? The hardest part of these is solving the inequalities. Because when you get like roots and cube roots and stuff, it's like, yeah, let's look at this one. Okay. And if you have issues trying to solve something, graph it, right? Choose a graphing software, look at the picture, right? That'll help you resolve. You'll check your work that way. So let's see, g prime is going to be 1/3 x to the minus 2/3. The g double prime is going to be negative 2/9 x to the minus 5/3. So if you're looking at this and you're like, when is this positive, right? This is when you need to remember the differences between even roots and odd roots, right? Remember, like, you can't take the square root of a negative number, like x has to be positive here. And that's true for any even root. And that's because 2 squared is the same as negative 2 squared is 4, right? So if you're trying to do the root, trying to go the other way, you don't know which one it comes from, right? It can only be one for it to be a function, so we already say it's this one, right? We restrict ourselves to positive values for even roots. But for an odd root, you don't have this issue because negative 2 cubed is negative 8. Positive 2 cubed is positive 8, right? So the odd roots, they are invertible. You could take the cube root of x, and x doesn't have to be restricted to positive numbers, right? Now remember that? It's a subtlety that's easy to forget. This is an odd root. So you can plug negative numbers into this, right? And if you're taking it to the 5th power, right, you're going to still get a negative number because there's an odd number of minus signs. So when is this positive? Well, this thing is negative. So this thing is only positive when this is negative, right? And that's only going to be negative, well, when x is negative. So that's the hardest part of this problem, right? So when x is negative, it's concave upward. That means that when x is positive, it's going to be downward. So when x is negative, the second derivative is positive. And when x is positive, the second derivative will be negative. So that means at 0 is an inflection point. Is that okay? Manageable? Okay. Let's look at C here. Well, quick note, when x is 0, this thing's undefined, right? Can't divide by 0. That tells you in this case it's an inflection point. This one has the picture. X to the 4th. Okay, h prime is 4x cubed, so h double prime is 12x squared. So when is that positive? It doesn't matter what value of x you plug in because you're squaring it, right? This is positive for all x except for 0. If you let x be 0, you get 0, right? So this thing is, since this thing is always positive, right? It's always concave up. which you can see in the picture here. But again, what about zero? The second derivative is zero at zero. So right there at that point, they wouldn't say that it's concave up at a point. But what does that even mean? Like, here's a point. Is that concave up or concave down? That doesn't even make sense, right? You have to have an interval. So just because it's zero here, all right, the second derivative is zero, that doesn't mean it's an inflection point, right? It's concave up everywhere, right? Because this thing is positive for positive values of x, this thing is positive for negative values of x. And then it just happens to be zero at zero, okay? So be careful, just because the second derivative is zero, that doesn't mean it's an inflection point, right? If it goes from up to down or down to up, then you have an inflection point. But if it's up and then zero and then up, it's not an inflection point, right? That's this. All right, Sirius Radio. So revenue in millions from the period 04 to 15. X equals 4 is 2004. You can use 12.1 to show it's increasing throughout this period. What that means is if you take the first derivative, it's positive for all x between 4 and 15, right? If we took the derivative of this, we would have negative 12x squared plus 216x minus 440. And if we wanted to, we could ask, when is this positive? And we would find it's positive for 4 to 15, maybe more, all right? But they want us to find when is it concave upward or downward. Well, we need to take second derivatives. So we get negative 24x plus 216. So when is this concave upward? Well, it's concave upward. And I just subtract 216 from both sides. Now, if I multiply both sides by a minus, this thing has to flip-flop. Remember, that's how inequalities work. You multiply both sides by a negative, inequality flip-flops. Or if you take the reciprocal of both sides, inequality flip-flops. So x has to be less than 216 over 24. I forget what that is. 9. I think it's 9. So when x is less than 9, the second derivative is positive. That's upward, right? So that means that when x is greater than 9, this thing is downward, right? Because this thing, if we solve the inequality for less than, we would find the opposite here. So since it's going from up to down at 9, we have an inflection point. Blah, 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 blah. So here's a picture of it. We have time to like read their little paragraph here. So when in doubt, graph it, right? You can see it's concave up, then concave down, and then at 9 here, we have the point of inflection. All right, that's when the revenue. So at that you plug in 9 into your original revenue function, and you see you get that's the revenue for year 9, 2009. Practical terms, we know that revenue was increasing throughout this whole period. So this means the revenue was increasing at an increasing rate up until 2009. After that, it was increasing at a decreasing rate. All right, tongue twisters. The math is simple, putting it into words, paragraph, right? Why we like math, right? So simple concepts could be represented in simple terms in our minds. Without the math, it's really hard to think about a whole lot of stuff that our mind is totally capable of dealing with. Unemployment, ew. see what this column has to say. Unemployment rate rose rapidly after the 2008 recession before starting to decline, falling from 9.8% to 4.9%. For these years, the employment rate can be approximated using this function f of x. So from what years? 2010 to 2016. So this function is only valid in these years, in x. Outside those years, this function probably falls apart, right? It can be shown f of x is decreasing throughout this period. Yeah, if you took the first derivative, you looked at the inequality, you see that it's negative for x equals 10 to x equals 16. Find and interpret the point of inflection. So the point of inflection is going to be possibly where the second derivative is 0, right? Not necessarily. Or where the second derivative does not exist. So first off, we need to get our derivatives going, right? So I don't know what 3 times 0.045 is. 0.045 times 3. That would be 0.135. Okay, 1.755 times 2, 3.51, and 21.6. All right, no, I'm missing an x. Oop. There we go. So the second derivative, 0.135 times 2, 0.27x minus 3.51. So we want to find the point of inflection. Well, this thing is always defined for all values of x, so we don't have to worry about it not being defined somewhere, right? That could be the point of inflection. So we set this equal to 0 and find when this is due to 0. So 3.51, so x is 3.51 over 0.27. 2.51 divided by 0.27. 13. So in the year 2013, seems like we have an inflection point, right? So we want to make sure, right? Because we had that example up here where the second derivative was 0, right? But it wasn't an inflection point, right? Well, you can kind of tell that the way this thing works is this. Let's see. If I plug in a negative number, if I plug in a number less than 13, this is going to be negative. If I plug in a number bigger than 13, this is going to be positive. So it is an inflection point, right? Does that analysis make sense? Yeah? All right. And here's our picture. All right, so you can see it is a point of inflection. Might be kind of hard to tell. Like if you graphed it and you didn't zoom in appropriately, that might look like a straight line, you know. The law of diminishing returns. Means if it's doing this, eventually it could do that, right? Or it'll plateau. If you have a horizontal asymptote, it'll stop increasing altogether, right? Depending on the function. The point of inflection is called the point of diminishing returns. It's where the rate of increase and increase begins to decrease, right? So the inflection point, that's your point of diminishing return. Right, All right, the revenue generated from airline passengers related to the number of available seat miles, X, seat miles. Interesting, isn't it? So here's our revenue. X is measured in hundreds of billions of miles. R of X is in billions of dollars. Is there a point of diminishing returns for this function? Well, you find the second derivative, set it equal to 0, solve, and make sure it's an inflection point, right? That's how you know. So instead of doing all this, let's just look at their answer. So they take the first derivative, take the derivative of that, make it pretty, right? Set it equal to 0, solve for X. Then they do a test. They use a test a number in the interval. So what they're doing there is they're trying to see if it's an inflection point or not, right? The second derivative here is they're finding out when it's positive and when it's negative. So at 11.31, right, is it positive or negative on each side of this thing, right? We did the other ones just by thinking about it, right? Another way is to pick a test point, like pick a number like 10 and plug it in and see if it's positive or negative, right? So our change from positive to negative. So they say it's positive over here, negative over here. So you could do a test point like 12. Plug 12 into this, and you're going to get a negative number. So that tells you the second derivative is negative over here. But again, since it's going from positive to negative, that's an inflection point. Positive is concave up, negative is concave down. So we're looking at something like that. So let's this is your inflection point for the second derivative. So you're going from concave up to concave down. That's our first rule. Let's look at our graph. They don't give us a graph that sucks. Let's see the graph. Okay, so now we have the point at 11.31. To figure out what our revenue is, we plug in 11.31 and find out what our revenue is. Increasing capacity beyond 1.131 trillion seat miles would not pay off. Maxima and minima. There's too much in this section. All right, so we'll have to come back to this next time. This section is too long to do in one class. All right, folks. Good luck on the quiz. I'll see y'all Friday.